In our final tutorial, we will be able to evaluate sigma notation. So let's flip over to this page in our notes, and we're talking about sigma notation. A synonym for sigma is summation. Basically, we're talking about a series of numbers. That means that we're adding them all up. We're talking about a sum. Now, looking at the page, don't be afraid if it looks like we're starting to talk Greek, because we actually are, okay? This sigma notation represents a Greek letter, capital sigma. And the sigma notation symbol is pretty easy to understand. There's three parts. The first part is this expression. This is the expression. This is basically the rule that we were talking about in a previous tutorial. And the bottom piece, where it says k equals 1, this is called your lower bound. This is the first number to plug in. And we're going to plug it right into the expression. So we plug in a 1 to find the first term, and then a 2, and then a 3, and then a 4, and then a 5, and then a 6. And this upper number, this is the last number to plug in. And again, we'll plug it right into this expression. So we plug in every number from the first number down here to the last number up here into this expression, and we get all of those terms, and we add them up, and we have our sum. So it's pretty easy to decipher this sigma notation. So it says evaluate. That means that we're finding the value of the sum. And in this case, our expression is 1 plus k squared, and we're starting by plugging in a 3, and we're stopping by plugging in a 6. So we're going to plug in a 3 first. 1 plus 3 squared. Well, 1 plus 3 squared would be 10. And then we're going to add to that. Let's plug in a 4. We'll plug in a 4, we get 1 plus 16. So that would be 17. And then we plugged in a 3, we plugged in a 4. Now let's plug in a 5. Plug in a 5 and we get 1 plus 5 squared. That's 26. And then we plug in a 6, but that's the last number we're going to be plugging in. So we've got the 3, the 4, the 5, and the 6. And we plug them all in. What is this? 6 squared plus 1? That's 37. Adding all 4 of these terms together, and we get 90. And that's our final answer for our sum. Now, I knew that there were going to be 4 terms because we have to go from the 3 to the 6, including the 3. 3, 4, 5, 6. Some people try to just subtract these numbers to figure out how many terms there are, but that's always going to be 1 less than the actual number of terms. So 6 minus 3 is 3, but don't forget that you're including the 3, so there are 4 total terms here. How many terms will there be in this sum? Well, this time I'm starting with a 0 and going to an 8. So 0 and then 1, 2, 3, 4, 5, 6, 7, 8. That would be 9 total terms. And let's see if we can find them. I'll start by plugging in a 0, and I'll have 1 over 0 factorial. And then I'll have 1 over 1 factorial. And then 1 over 2 factorial. And so on and so forth, all the way up to 8. So let's write all of these down. We got 5 factorial, 6 factorial, 7 factorial, and 1 over 8 factorial. So there are our 9 terms. 1, 2, 3, 4, 5, 6, 7, 8. We do have 9 terms. Now let's see what all of these terms are so we can add them together. So 1 over 0 factorial, remember 0 factorial is defined as a 1, so this is 1 over 1. And this is actually also 1 over 1. And this is 1 over 2. 3 factorial would be 3 times 2 times 1, which is 6, so this is 1 over 6. 4 factorial would basically be 3 factorial times 4, so 6 times 4, which is 24. 5 factorial, 5 times 4 times 3 times 2 times 1, we've already done that, is 120, which is 24 times 5. 120 times 6 would be our next one, which would be 720. 6 factorial. 7 factorial would be 720 times 7, which is 5040. And 8 factorial, our last one, would be 5040 times 8, which would be 40,320. Okay, so now we add all of these fractions together. I would probably do it on my calculator. And if you plug all of these fractions into the calculator, you get approximately, we'll go to 3 decimal places, 2.718. Now, I wonder if this rings a bell. Isn't this a number that we've learned before? This is very close to the number e. And in fact, this is yet another way to calculate e. Now, obviously, this is not equal to e because e is an irrational number. It goes on forever. So if we knocked this 8 onto its side and actually talked about infinite terms, instead of just 8 or 9 terms, I guess, but instead of stopping by plugging in an 8, if we kept going on forever and added up these infinite fractions, we actually would be equal to e. So that's kind of neat. Right now, the answer was approximately 2.718, but if we went on forever, which would take a long time, we'd get exactly to e. Now you might say, well, that's impossible. We can't be here forever adding up an infinite sum. Uh-oh, look at our final example. I'm going to add up infinite terms from 1 to infinity and see if I can figure out what this sum is. And yes, this can be done. Let's see if we can figure out a pattern. So we're going to be plugging in a 1, of course, first. So we get 3 over 10. Okay, great. Let's add to that. Let's plug in a 2. And of course, 10 squared would become 100. So we're talking about 3 over 100. And then plugging in a 3, we'd get 1,000. So this is 3 over 1,000. And then plugging in a 4, we'd get 3 over 10,000. Basically, every time we add a degree, we're adding a 0 to the denominator. So we'd get 3 over 100,000 next. And of course, if this is going to go on forever, well, that's going to be impossible for us to actually write all infinite terms. But let's see what these are. I know what 3/10 looks like. That's 0.3, maybe as a decimal. 3 100ths is 0.03. 3 1,000ths is 0.003. 3 10,000ths is 0.0003, and so on and so forth. I'll do one more, 0.00003. And if we added all of these together, we would have this 3, and then this 3 in the second spot, and then this 3 in the third spot, and then this 3 in the fourth spot, and this 3 in the fifth spot, forever and ever and ever. And we know what that number is. It's 1/3. Crazy. So we can add up some infinite terms. So when I think of a problem like this, where we have infinite 3's and that's equal to 1/3, this rational number, it always makes me think of this question. And this is a pretty famous debate among math teachers, and all teachers really. Does the number 0.9 repeating equal to the number 1? That's my question. And if you'd like to explore this with me, I'd invite you to the next tutorial. It's kind of a bonus tutorial, but if you have your thoughts as to whether these numbers are equal or whether they're not, I'd like to talk about that in the next tutorial. Thanks for watching this one, and hopefully I'll see you in that bonus tutorial. Either way, I'll see you in class. Bye-bye.